A lot of people underestimate just how much the Soviet Union contributed to the technological revolution of the 20th century. The Soviets ignited the space race. They built the first orbital rocket that led humanity's way into Earth orbit and beyond. But they didn't stop there. That was only the beginning of a decades-long story that saw nuclear missiles become spaceships. It would lead the Soviets to build the biggest and most powerful rockets the world had ever seen. There would be glorious success, there would be explosive failure, and all of it framed by the rise and fall of a global superpower. These are the rockets that the Soviet Union built along the way, a story of human space exploration, a beginning but not necessarily an end. These rockets are not done yet. First, we have to talk about the R-7, also known as Semyorka, easily the most important rocket in Soviet and Russian history. There's a case to be made that this is the most important rocket in the entire history of space exploration. It was there at the beginning, and it is still launching people into orbit today. As you can probably tell from the name, this was the 7th in a series. The R stands for rocket, and these designs actually began as long-range missiles in the 1940s. The Soviet R-1 was a direct copy of the German V-2 ballistic missile. It was good, but Joseph Stalin wanted better. And in 1953, the Soviets began development of the R-7. This is more than just another weapon of war, it's destined to become the world's first intercontinental ballistic missile, a machine with truly awesome power and the capability to fly over thousands of miles, carrying a 3-ton nuclear warhead. This was a rocket that could end the world. Not to say that the Soviets actually wanted to trigger a nuclear apocalypse, they just wanted everyone to know that they could do it. That's the Cold War in a nutshell. Anyway, to build the monster, the Soviet Union called on 2 of their greatest engineering minds. One was Sergei Korolev, the father of the Soviet space program, and a founding father of the entire space race, honestly. What he built was a monster for that time. The R-7 was more like 5 rockets all bundled together, 4 side boosters strapped to a center core, the first time that it had ever been done. And it allowed the R-7 to function as a 2-stage rocket, meaning that you could run all 5 engines at liftoff. Then, once you get above the atmosphere, you drop the side boosters and continue accelerating into space using your core engine as a second stage. This was the most simple way to achieve rocket staging because you don't have to worry about igniting a second engine in mid-air. But that doesn't mean this was easy. Korolev had to design a system that would perfectly balance all 5 engines from the moment of ignition all the way through the flight path. If any one of those 4 boosters ran just a little too hot or a little too weak, then the entire rocket would be thrown off course. Korolev is maybe best known for the booster separation system he designed for the R-7. They need to jettison all 4 of the side boosters at exactly the same moment. Again, any unbalance will throw the second stage off course. So what we get is this amazing synchronized ballet of rocketry. After the booster engines cut out, an anchor is released at the base of the rocket. That allows the boosters to flare out at the bottom with a hinge at the top. Then a small thruster at the tip of each booster fires to push off from the core and send them all into a perfectly synchronized backflip. As the boosters fall away, they keep flipping in this perfectly symmetrical cross shape, something that will forever be known as the Korolev cross. Now, none of this would be possible without some truly amazing engines, and that's where the Soviet founding father number 2 comes in, Valentin Glushko, the engine man. To get such a humongous rocket off the ground, they needed a powerful new engine. Glushko had been expanding on the German V-2 engine design, making it bigger and more capable, but there's a limit to the physical size of a rocket engine. A bigger combustion chamber means a bigger combustion, and at a certain point, that gets difficult to manage. The engine just tears itself apart. But Glushko had a solution. Instead of building one large combustion chamber, he split the engine into 4 smaller chambers, each with their own nozzle, so it might look like the R-7 boosters have 4 engines, but it's actually one engine with 4 nozzles. By distributing the energy across more surface area, this increased the stability and reliability of the rocket. And that is the foundation of the Soviet space program. Luckily for everyone, the R-7 was never used as a nuclear missile, and in October 1957, it deployed the first ever satellite into Earth orbit, Sputnik 1. Then just 1 month later, it launched the first animal into orbit, Laika the dog, RIP. Then it launched this crazy thing into space that the Soviets called Object D. But they weren't satisfied with just putting stuff into Earth orbit. The Soviet leader Nikita Khrushchev saw how the world reacted to his nation's dominance over outer space. The Soviets had ignited a space race and they were winning, but now they had to keep winning. So they aimed for the moon. The first evolution of the R-7 design came in 1958. Luna was specifically designed to send a payload to the moon. Again, still no computers at this time, so they had no illusions about being able to land on the moon. But the Soviets were pretty sure that they could smash something into it, and that still counts for something. To achieve this, Korolev adds a third stage to the R-7. Glushko designs a small single-nozzle engine that can be ignited in the vacuum of space and provide enough thrust to send a small object from Earth orbit into a collision course with the moon. Luna 1 missed the mark. It sails past the moon and becomes the first man-made object to escape Earth orbit. It's still out there today, floating around between Earth and Mars. Luna 2 hits the bullseye and becomes the first man-made object to impact the moon. And then, to take it up a notch, the Soviets send Luna 3 with a camera to fly past the moon and take the first ever photograph of the far side, a view that no human being had ever seen before. This is where things get real. A human-rated version of the Luna rocket. Same R-7 booster section, but it's been reinforced to support a heavier payload, which is now a capsule for the first man to ever fly to space, Yuri Gagarin. This was achieved in April 1961. The Vostok rocket also launched the first woman into space, Valentina Tereshkova, in 1963. By this point, the Soviets had already achieved incredible things. They were dominating the space race, but Korolev wanted to go further. He knew that his rocket could send payloads to other planets. Molniya was an interplanetary upgrade to the R-7 platform. Again, the booster was largely unchanged. The structure was beefed up a little bit, and it was given more power. Then, Korolev and Glushko added a fourth stage with an engine that could be restarted multiple times in flight. This was necessary to navigate the orbital dynamics of the solar system. But cracks were beginning to show in the Soviet design. They may have started pushing the R-7 beyond its limits. Out of 12 Molniya launches, only 2 were successful. They managed to get one probe on its way to Mars and another probe on its way to Venus. Neither of them successfully reached their destination. While the Molniya might not have been very good at the job it was intended for, that R-7 variant would be repurposed into an even more important role, Voskhod. They removed the interplanetary fourth stage and replaced it with an expanded crew capsule that could now fly multiple people into orbit. This allowed Alexei Leonov to conduct the first ever spacewalk in 1965. This is the final evolution of the R-7 rocket family, Soyuz. Again, it's a little bigger and more powerful than before, but still largely unchanged from that very first nuclear missile in the mid-50s. The crowning jewel is the Soviets' most advanced spacecraft yet. The Soyuz capsule can carry 3 people into space, it can maneuver in Earth orbit, dock with other spacecraft and space stations. The Soviets even believe that this vehicle can fly people around the moon. But we are into the year 1966 now, and the space race is evolving. The Americans are catching up fast, and the pressure is on the Soviet Union to stay competitive. To make matters worse, 1966 is also the year that Sergei Korolev dies suddenly from an illness. It leaves the Soviet space program in a bad spot, and that's made clear by the disastrous introduction of the Soyuz rocket. Soyuz 1 spins out of control shortly after launch. Soyuz 2 explodes on the launch pad, and based on that track record, they make the decision to strap a poor soul named Vladimir Komarov into the pilot's seat of Soyuz 3. Komarov's parachute fails to deploy on the capsule's return to Earth, and he becomes the first person to die on a spaceflight mission. That, combined with another significant post-Korolev failure that we'll talk about in a little bit, really took the wind out of the Soviet sails. The Americans pulled ahead, they landed on the moon, and the space race was won. But the Soviets did not stop. They kept working on their rocket design, and in 1973, the Soyuz U was launched for the first time. It had upgraded booster engines and a more robust upper stage that proved to be incredibly successful and reliable for human spaceflight. So reliable, in fact, that it's still used to this day. Soyuz has launched hundreds of times, it's sent dozens of crews to the International Space Station, and it's currently one of only 2 operational human-rated spacecraft in the world. The only significant change made to Soyuz over the years was a refit in 2004 that converted the internal systems from analog to digital. Now, the R-7 and Soyuz design was fundamental for the Soviet space program, but it was not their only rocket. There's an unsung hero of the space race, and it's known as the Proton. Much like the R-7, Proton was originally conceived as a weapon of mass destruction. This was the mid-1960s, and the nuclear arms race had escalated to the point where both the Americans and the Soviets were building bigger and bigger bombs. This is how we ended up with things like the Tsar Bomba, the most powerful nuclear weapon ever detonated. But these giant bombs are essentially useless without an equally giant missile to carry them. This is where Proton comes in. It was not a Sergei Korolev design. This one was handed off to Vladimir Chaloemy, a rival to Korolev, but again, the engine design was provided by Glushko. Only this time, he went with something totally different from the complex multi-chamber system that he'd used on the R-7. Proton was all about maximum power and simplicity, a brute force approach. So the R-253 engine was a single combustion chamber, a single nozzle, and a very different fuel source. Proton is a hypergolic rocket, which means that it uses a self-combusting fuel. When you combine a chemical called hydrazine with an oxidizer called nitrogen tetroxide, you get instant combustion. No need for an ignition system. And these hypergolic propellants store an incredible amount of energy. So not only does it simplify the rocket, but you also get the most potential thrust. Sounds great, right? So why doesn't everyone use this stuff? Well, it's also incredibly toxic. If you even just breathe the fumes, your lungs will melt. But considering they were building this rocket to nuke the entire planet, the Soviets probably didn't pay much mind to the toxic exhaust. Luckily for us, the proliferation of gigantic hydrogen bombs quickly fell out of style after both sides realized they didn't actually want to trigger an instant apocalypse. So just like the R-7, Proton was quickly adapted to spaceflight, and the incredible power of this machine really opened up some possibilities. The first stage had 6 side boosters, but unlike the R-7, there was no engine in the middle, so when it came to the first separation, they didn't backflip gracefully. The rocket just dumped the lower half, and this happened at the same time that the second stage would fire up another 4 engines and blast into the top of the booster core. This is called hot staging, and it helped Proton to maximize thrust even further. Since that first launch in 1965, Proton has become the heavy-duty workhorse of the Soviet and Russian space programs. Proton is what allowed the Soviets to begin the first experiments with long-term space stations with the Salyut program in the 1970s. Proton launched the first probe to successfully land on Mars in 1971. At the same time, it also launched the first probe to successfully land on Venus. Then it landed half a dozen more probes on Venus. Proton was used to put the Mir space station into orbit, and it also launched the first module of the International Space Station. Proton got an upgrade in 2001 with a more efficient and accurate navigation system and a more powerful booster stage. It continued on as the most powerful rocket in the Russian fleet with a capability to put around 24 tons into low Earth orbit. In all, Proton has launched over 400 times, with 49 of those being unsuccessful. So it's not exactly famous for reliability, but it still delivers on power. For all its might though, Proton was far from the most powerful Soviet rocket. This was Sergei Koryolev's final contribution to the Soviet Union, a genuine monster of a rocket, the N-1. This was never intended as a weapon. This design was made specifically to win the space race, a moon rocket that would put Soviet boots on the lunar surface before the Americans. Development of the N-1 began in 1963, and needless to say, this thing was ambitious. The booster stage had 30 individual engines, but the NK-15 rocket engine was not a Glushko design. The legendary partnership between the two founding fathers of the space race had been broken by an argument over how to power the N-1. Glushko was pushing to use a hypergolic rocket engine, while Koryolev wanted to continue with the same fuel as the R-7, liquid oxygen and kerosene. This was nothing new. These two had butted heads for a long time. It's even said that back in the 1930s, Glushko had leaked false information to Stalin's secret police and got Koryolev locked up in the Gulag for a year. So, with a relationship like that, a falling out was inevitable. Not that it really mattered in the end. Koryolev died before the first N-1 was fully completed, and by the time the rocket was finished, the Americans had already launched their own giant moon rocket, the Saturn V. The Soviets were losing, but they pressed on. If the N-1 could work, they'd have a chance at pulling themselves back into the lead. When the monster rolled out to the launch pad for the first time in February 1969, it stood 105 meters tall, an incredible 17 meters wide at the base, and packed significantly more thrust than any other rocket ever made. The N-1 held the record for the most powerful rocket right up until SpaceX launched their Starship in 2023. Unfortunately, for all its power, the N-1 was equally as chaotic. The first test flight exploded in mid-air at an altitude of 12 kilometers. The second test flight in July 1969 got only a few meters off the ground before it stalled out, fell back down, and triggered the largest non-nuclear explosion in human history. 2 weeks after the second disaster, Neil Armstrong and Buzz Aldrin walked on the moon. But the Soviets were not deterred. In 1971, they were back on the launch pad with a third N-1. It flew for 51 seconds before it also exploded in midair. And somehow, after all that, the Soviets did not give up. In November 1972, they had yet another N-1 on the launch pad, and this time it flew majestically all the way up to an altitude of 40 kilometers. And the first booster engine cut off when, you guessed it, boom. And that was the end of the Soviets' ambition for landing on the moon, but it definitely was not the end of their rocket-building endeavors. Far from it, actually. Going a little bit smaller now, Cosmos was another rocket derived from an early 1960s ballistic missile. It had a relatively low payload capacity of just under 1.5 tons, but Cosmos was used heavily to deploy Soviet military and reconnaissance satellites. The rocket launched over 420 times until retirement in 2010 and had a success rate over 99%, making it one of the most reliable rockets ever made. Development of the Zenit rocket in the early 1970s marked the beginning of a new chapter for the Soviet Union. Moving on from the space race and competition with America, they began to develop the next generation of Soviet rocket. The idea was a highly versatile launcher, something more powerful than Soyuz and more environmentally friendly than Proton, with a payload capacity somewhere in the middle. Unfortunately, the development process was slow. The first launch didn't come until 1985, so it never really got a chance to gain traction as a Soyuz replacement. But the rocket did fly around 36 times. The Zenit 3 was actually launched from a floating platform in the Pacific Ocean. This allowed the Soviet rocket to lift off from Earth's equator and gain extra momentum from the planet's rotation, making it easier to put satellites into extremely high geostationary orbits. Probably the most interesting thing about Zenit is that in addition to operating as a standalone rocket, this could also be adapted as an ultra-powerful side booster for the pinnacle of Soviet rocket science. It was the mid-1970s, and Glushko was in charge of the Soviet space program now. He was given an incredible task: build a successor to the failed N-1, a super-heavy booster that would match NASA's Saturn V moon rocket, but it also had to serve a dual purpose as a launch platform for the Soviets' own space shuttle, Buran. They knew that the Americans were developing a fleet of reusable spaceplanes, and the Soviets decided that they were gonna do it too, but bigger and more powerful, the Soviet way. The project was named Energia. It would use 4 Zenit rockets as strap-on side boosters, each one equipped with an RD-170 engine, Glushko's evolution of the old RD-107 from back in the 1950s. The same general design with 4 combustion chambers, but Glushko pushed this one to the absolute limit, creating the single most powerful rocket engine in history. Those were strapped to the Energia's center core, which itself was loaded with 4 big engines, the RD-0120. They burned liquid hydrogen from the rocket's massive center tank, the first Soviet booster stage to use hydrogen fuel. What Glushko ended up with was a high-powered, high-efficiency rocket that could deploy up to 100 tons into low Earth orbit. Since NASA had already retired the Saturn V, that made Energia the most powerful and most capable rocket in the world. And it worked too. Unlike the N1, Energia flew successfully on its first test launch in 1987 and deployed an 80-ton payload into space. The payload itself failed to reach orbit due to a computer glitch, but considering this was later revealed to have been an orbital weapons platform equipped with a giant space laser, it's probably for the best that it didn't work. Energia flew a second time in 1988, and it successfully deployed an unmanned Buran space shuttle into orbit. Unfortunately, this all came far too late for the Soviet Union. Not only had the Americans launched their own space shuttle 7 years earlier, but the massive Soviet nation itself was beginning to come apart at the seams. Glushko died a year later in 1989, the same year that the Berlin Wall was torn down. Then, in the early 90s, the Soviet Union dissolved back into a collection of independent nations. Russia inherited most of the space program, but all of these new lines on the map had led to complications. A lot of the rocket hardware was being manufactured in what was now Ukraine. Their primary launch pad was in Kazakhstan, and there was a lot less money going around to fund things like giant rockets and spaceplanes. So Russia scaled back. Energia and Buran were dead in the water. Instead of trying to replace the already ancient Soyuz, Russia just kept that ball rolling. Zenit was a great idea, but they didn't have the resources to finish developing it. Proton was not an ideal rocket, but it was the most powerful vehicle they could afford to keep, so it carried on for heavy missions. But that is not to say that the Russians didn't build anything new. The name says it all. Voskhod was nothing fancy, but it was an effective 90s-era Russian design that adapted an old, decommissioned ballistic missile into an orbital rocket, part of a post-Cold War initiative to convert surplus weapons of mass destruction into satellite launchers. Another 90s design that was part of a cooperation between Russia and Ukraine, it was adapted from an old ballistic missile named the SS-18, which carried the nickname Satan due to its ability to deploy up to 10 nuclear warheads onto different targets in one launch. That technology proved pretty useful for deploying multiple satellites into space. The Dnieper also launched out of an underground tube just like a nuclear missile. This is probably most famous as the rocket that Elon Musk tried to purchase from the Russian military back in 2001 when he had the idea to launch a greenhouse to Mars. The Russians refused to sell Elon a rocket, so he decided to go home and build his own. This is the first rocket fully designed, manufactured, and launched in Russia, the Angara. The concept was for a modular launch system that could fly as a single-core rocket for small satellites, but could be fitted with up to 6 strap-on boosters for a maximum payload capacity of 40 tons to low Earth orbit. Each booster was equipped with a new rocket engine, the RD-191. Based on Glushko's design for the RD-170 in the Energia booster, they simplified the design down from 4 combustion chambers to just 1. The Angara rocket system would finally provide a modern replacement for both the Soyuz and the Proton. But progress has been slow. After more than 20 years in development, the first single-core Angara launched in July 2014 as a suborbital test flight. That was quickly followed up in December 2014 with the first launch of an Angara 5 with 4 side boosters. The rocket was able to deliver a dummy payload into low Earth orbit. And then for a long time, nothing happened. It wasn't until December 2020 that another Angara 5 was brought to the launch pad for a second test flight. Then the A5 launched again in December 2021. After another long pause, the Angara 5 lifted off for a 4th time in April 2024, ending the rocket's testing phase and clearing it for full operation. That began just recently in June 2025. Russia launched the Angara 5 with a classified Air Force satellite on board that was deployed into geosynchronous orbit. Stuff like this can easily get lost in the unrelenting global news cycle, but all this time that the Russians have been fighting a war against Ukraine, they've also been finalizing the development of their most powerful rocket since the Soviet Union. And they have big plans for Angara. In 2028, Russia wants to launch the first crewed capsule to the ISS using an Angara 5 booster, and in the same year, they've also planned to launch a robotic moon lander with the A5. Then a lunar sample return mission in 2029 and a lunar rover in 2030. Now, whether or not the Russians can actually follow through on those plans, given the current state of things, that's debatable. Though it's not like a country has never fought a war and gone to the moon at the same time. Just look at the Apollo program, which carried on through the peak of America's Vietnam War. The story that these Soviet engineers began 70 years ago is still carrying on to this day, and I wouldn't count them out just yet.